Okay guys, welcome back. So in the last video we talked about the conservation of linear momentum, and I explained as to how the linear momentum is conserved for a system. So in this video I'll be taking some examples in which the conservation of linear momentum can be applied and explain to you how they can be solved. So in the first example I'll take a simple object like this. Two objects actually. This is a simple plane, and this has some, say, 2 kg object, and it has some velocity that will take 10 meters per second. 10 meters per second. And this collides with another object of mass 4 kilograms. Which is initially at rest. So at the collision I can draw the forces, the impulse and the impulsive force in which the two objects the time of collision actually. So these two objects collide like this. So according to Newton's third law, the two forces should be equal, and therefore the two impulse should be equal, because the force exerted by this object to this object is an external force. I would say this is object A, right? This is object A, and this is object B, and this is A, this is B, this is 2 kilograms, this is 4 kilograms, like that. Now the external force applied by the object A to B, so that's an external force to B. I'll take it as F, should be equal to the external force applied by B on A, because the two forces should be equal by Newton's third law. So if the two forces are equal, two impulses should be equal as well, because the time they have the impulse is equal. So I'll directly draw the two impulses in this motion. This as I, like that, and I'll take the final velocities as v1 and v2. This is 2 kilograms, this is A, this is 4 kilograms, this is B. So we want to find V1 and V2. So actually I'll take this as a completely elastic collision. So if this is an elastic collision, we can simply put the conservation of mechanical energy or conservation of energy. So I'll first of all say that this force, this impulse is equal to this impulse. I told you that the two forces acting upon this object are equal. So when you consider the whole system at any moment, you can see that the total external forces cancel each other. The external forces cancel each other, and the total external force is 0. So you can simply put the conservation of linear momentum. So in the conservation of linear momentum, if you are not watched my previous video, I invite you to watch that video and come back and watch this video, because it will be easy for you to understand this concept. So in the case of linear moment, conservation of linear momentum, you can say if the total external force on the system at any moment is 0, you can say that the momentum, the total linear momentum at the initial position is equal to the total linear momentum at the final position. So it's simply like this. So the total linear momentum at the initial position I will take as Pi is equal to Ps. So this is from the conservation of linear momentum. Conservation of linear momentum, right? Conservation of linear momentum. I can say Pi equals Pf. So the only momentum that happens at the initial position is the momentum due to the velocity of the 2 kilogram mass, because the 4 kilogram mass is initially at rest. So the initial momentum is mv m is 2 kilograms, the velocity is 10 meters per second, so the initial momentum is 2 times 10, that is 20, so that is in this direction. We have taken the direction because the momentum is a vector. So 20 in this direction. So we have velocity v1 in this direction for the 2 kilogram mass and v2 velocity for the 4 kilogram mass. So both these velocities I have marked in the positive direction. I will take the positive direction in this direction in which the objects are moving at the initial position and at the final position. Now sometimes v1 and v2, either v1 or v2 or both v1 and v2 may be going in the opposite direction. If so, we will get v1 and v2 or which are the quantity that is moving in the other direction as minus. So for now I will take both the objects moving in the direction that the initial momentum was present, so that the initial momentum was in this direction, the initial velocity of this object, so the initial momentum was in this direction. I will take the objects after collision also in this direction. Alright, so the mass of the object is 2 kilograms, so its momentum will be 2 times v1, and this object B's mass is 4 kilograms and its velocity is v2 meters per second, so its momentum will be 4v2. So 2v1 and 4v2 are both in this direction, so they will add up. So final momentum will be 2v1 plus 4v2. Now this is because this is in the same direction, we don't have to take actually the vector quantity, we can directly write, we can divide it by 2. So this is 10 equals v1 plus 2v2. So that's the first equation that we are getting, 10 equals v1 plus 2v2. So I told you that this is an elastic collision. So in the last video I told you that if two or more objects collide in an elastic collision, their total kinetic energy is conserved. Since the total kinetic energy is conserved, you can say that the kinetic energy at the initial position is equal to the kinetic energy at the final position. So I can say from conservation of energy, I can say Ke, that's the kinetic energy, initial position is equal to the kinetic energy final position. Kei equals Kef. Alright, so the only kinetic energy at the initial position is due to the mass and the velocity of A. Only mass and velocity of A, because mass of B, although B is initially at rest, so it doesn't have any kinetic energy. So the initial kinetic energy of this system is half times the mass 2 times the square of the velocity, that is 10 squared. So half times 2 is 1, 1 times 10 squared is 100. So the initial kinetic energy of this system is 100. This is 100. So this is equal to the final kinetic energy if the kinetic energy or the energy is conserved. So the final kinetic energy will be, the mass is 2 kilograms and the velocity is 1. So the final kinetic energy of A will be half times 2 times 1 square, that is V1 square. V1 square plus kinetic energy of B at the final position is half times the mass 4 times V2 square, that is half times 4 is 2, 2V2 square. 2V2 square. So this is equation 2. Now you have two unknown, now you know 10 equals V1 plus 2V2 from the first equation, and 100 equals V1 squared plus 2V squared from the second equation. Now you have two unknown terms, so you need two equations to solve this. Now you have two equations, so you need to substitute, because these are not the equations. One equation is an addition and the other equation is the addition of square of those terms. So you need to substitute one value from the equation 1 to equation 2 and then solve for one value, and then substitute that value to equation 1 and find the other value. So I will take equation 1 again. From equation 1 I can say, equation 1 I can say V1 plus 2V2 is 10, which is given. So I can say V1 is equal to 10 minus 2V2. V1 plus 2V2 is equal to 10. So V1 is equal to 10 minus 2V2. So I can substitute this value to 2. So I'll take this as 3. From 3 to 2, I can say 100 is equal to V1 square plus 2 times V2 square. So V1 we already know by now, 10 minus 2 V2, we can substitute that here, and V2 we have here, so we will have a quadratic equation of V2. Actually it's not a quadratic equation, it's actually a square of V2. We can isolate V2 easily and then find the value of V2, and then I will substitute that value to equation 1 and find the value of V1. Alright, so 100 equals V1 square is 10 minus 2V2 square plus this is already 2V2 square, right? So this is 100, 10 square is 100, this is minus 2 times 20, 20 times 2, 40 V2 plus 4V2 square plus 2V2 square because this one. So you can say this 100 to 100 cancel. So this is 6V2 square is equal to minus 40 V2, right? 6V2 square is equal to minus 40 V2. So V2 cannot be 0 because there should be some velocity. V2 is the velocity of B. So sometimes V1 can be 0, so that the whole kinetic energy is passed to V2. V1 can be 0, but V2 cannot be 0 because if an object is initially at rest and is guided by another object, that object should have velocity. So V2 cannot be 0, we can cancel one V2. So we can say V2 is equal to minus 40 by 6 is minus 20 by 3 or minus 6.6 meters per second. Right? So as I told you, there can be some instances in which the direction changes. So this is a good example in which the direction changes. So V2 is equal to minus 6.6 means that V2 is equal to 6.6, but the object is moving in the other way, in this direction. So we can substitute that value to equation 1 and find V1. So you can say 10 equals V1 plus 2V2. 10 equals V1 plus 2V2 from the equation 1. So 2V2 we know V2 is equal to minus 6.6. So 2 times V2 is minus 6.6 times 2, which is minus 13.2. So this is plus times minus 13.2 is minus 13.2. So V1 is 23.2. V1 is 23.2 meters per second. So V1 stays in the same direction. So V1 actually, what happens is V1 increases its velocity by colliding with V2, AA, actually the mass A, which is 2 kilograms, increases its kinetic energy by hitting with B because its velocity, the mass stays constant, but the velocity increases, so its kinetic energy increases. The kinetic energy of B also increases, but its direction changes. It's initially at rest, and we assume at the beginning that it will also go in the direction of A, but when we solve the sum and we got the final answer, we could see that B changes its direction and A goes in the same direction, B goes in the other direction. So this is a simple example to illustrate that the conservation of the conservation of linear momentum. So in the next example, I will take another sum in which the particles colliding with not in the same direction. So thanks for watching this video and see you then.